So in the previous lecture, we learned how to find the values of observables from the wave function. And we learned that sometimes there is only one value if it's an eigenstate, and sometimes there is a mixture of values, and we can still find the expectation value of that observable. But when it comes to finding the value of observables, we know there is a famous rule called the uncertainty principle in quantum mechanics, which says for certain variables, A and B, we are not able to find both A and B accurately. In other words, if there's only a single value for A, so delta A equal to 0, then delta B cannot possibly be 0, in fact will reach infinity. So A and B cannot be measured simultaneously with accuracy. Now what that really means is that it is impossible to find a state which is both an eigenstate for A and an eigenstate for B, because if that were the case, then there is only one measurement value for A and one measurement value for B, so both delta A and delta B will approach 0 simultaneously. So the uncertainty principle simply tells us that it's not possible for certain variables A and B. But we know that not all variables satisfy that. In fact, if you pick up Px and X, we know that these two variables indeed cannot be measured with accuracy, 100% accuracy simultaneously. So satisfy the uncertainty principle, the Heisenberg principle. But what about you pick up Px and K, assuming it only moves in X direction, so K is Px squared over 2m. Now if Px and K are both accurate, so it's simultaneous eigenstate, then there is no delta Px and there is no delta K. Is that possible? Of course it is. If you look at a free particle, that's exactly the case. For free particle, there is only one value for its momentum, and there is only one value for its kinetic energy, so both delta P and delta K would be equal to 0. Of course, the product is also 0. So for these two variables, they don't have any uncertainty principle to satisfy. So that begs the following question, and that is, if I pick up two arbitrary observables, A and B, how do I know that there is an uncertain relation between them? So I have to compromise the accuracy of one of them if I want to know better about the other one. And how do I know sometimes you don't have to worry about the uncertainty relationship? What is the general rule? Well, certainly this has to do with simultaneous eigenstates. Again, if I can find a simultaneous eigenstate for both A and B, then certainly there is no uncertainty principle between A and B. So let's see. We define a simultaneous eigenstate psi, here's the wave function psi, so that the operator A acting on psi gives you a number A times psi, and the same thing happens to B. Operator B acting on the same wave function will give you just a number times that wave function. Now again, it is clear that if that's the case, then delta equal to 0 and delta B equal to 0, because there is only one A value and one B value, so no uncertain principle between A and B. Example, like I said, free particles for Px and K. But can we always find simultaneous eigenstates given two arbitrary quantities A and B, two arbitrary observables A and B? Can we always do that? If we can always do that, then there would be no such thing as uncertainty principle between them, right? Certainly, we know that is not true. So the question is, when can we find simultaneous eigenstates when we cannot do that? To answer that question, we have a definition, a new definition to introduce, and it's called a commutator. A commutator is defined to be the product of two operators, A times B, minus the product of the same operators backwards, B times A. Now, clearly, if A and B are both just numbers, then this commutator will be equal to 0 because AB equals BA, right? But remember, we're not dealing with ordinary numbers. We're dealing with differential operators. So this commutator, it turns out, may not be 0. We'll see. Okay, so what is the condition for two operators A and B to have simultaneous eigenstate? Well, let's see here. For simultaneous eigenstate psi to exist, if that is true, if there is such a simultaneous eigenstate, then let us put this commutator operating on this simultaneous eigenstate psi, and let's see what happens. Okay, by definition, this is AB minus BA times psi, so it's AB psi times BA psi. Okay, here's the thing. When you have this operator, differential operator, will operate on everything after that, okay? Everything after that. And same thing here, this b operating on a, operating on both this operator and this wave function psi. So, but in this case, it's rather simple because b operating on psi is just a number b times psi, and a operating on psi is just a number a times psi. So I get a number here and I get a number there, right? Now, when you take a differential operator acting on a number, you can simply take the number out. So the first term becomes, you take that b out, b times a psi. The second one is a, number a times b psi, right? Now we arrive at operator a on psi and operator b on psi. By definition of simultaneous eigenstate, you can replace this a with a number a, replace this operator b with another number b, then this is b a psi minus a b psi, and that's clearly 0. So what does that mean? It means if you can find a simultaneous eigenstate for both operators a and b, then the commutator of a and b operating on this particular simultaneous eigenstate must be 0. Okay, that is the condition for simultaneous eigenstates to exist. The commutator acting on that state must be 0. Now the commutator is defined as AB minus BA. But isn't it true, you may ask, isn't it true that AB is always equal to BA? And therefore, the commutator is always equal to 0 no matter what? Well, it's not that simple. In fact, let's take a look at this famous example, our first example of the uncertainty principle, that is between px and x. X here is just a number, px is a differential operator. So let us find the commutator between the operator px and x. Let's see that. Okay, so here we have a defined as px, which is negative ih bar, partial x, as you know, the differential operator for the momentum in the x direction. And b is just a number, just x. Now, find the commutator between px and x. Let's do that. How do we find this commutator? Well, we're going to take that commutator, right? We're going to operate it on any arbitrary wave function. Okay, it's an arbitrary wave function, whether it's a simultaneous wave, simultaneous eigenstate or whatever, I don't care. It's just an arbitrary wave function. So I'm going to operate it on psi, which is an arbitrary wave function. And so you plug in px and x expression, and by definition, this is ab psi minus ba psi. Here, this is the differential operator for px acting on x psi, and here is x times the differential operator for px on psi. Now remember I said, whatever differential operator you have, it must act on everything after it. Okay, everything after it. So this differential operator works on both x and psi, but this differential operator works only on psi because x has been already taken out. It's ba minus, not ab. And let's see what happens if you did that. You take that ih bar out, right? So you're left with that. And clearly, this term does not cancel with that term because this term has, in fact, you work it out, there are two terms, right? There is x, then partial phi, partial x, and there's another term which is partial x over partial, which is 1 times psi. So there are actually two terms here, so that's what I worked out, right? And indeed, those two terms cancel, but you do have one term left, which is psi. And therefore, the commutator between px operator and x acting on arbitrary wave function is not equal to 0. Rather, it is equal to negative ih bar times the same arbitrary wave function. Negative ih bar. It is not equal to 0. This violates the condition that we just stated a moment ago, and that is for two operators to have the simultaneous eigenstate, they must have a commutator of 0 if we operate it on that particular simultaneous eigenstate. But here, you take that commutator between px and x, you operate on any wave function. You never get 0. You just get a constant negative ih bar times the same wave function. So that clearly violates that condition. Therefore, px and x cannot have possibly a simultaneous eigenstate, which means you cannot measure both px and x with 100% accuracy. So this tells us that the commutator between px and x is not 0, rather it's negative ih bar. In other words, they are non-commutative, that's what we say. If they're commutative, then you can switch the order of a and b when you do the product. So there's nothing new here in terms of mathematics. We learned that from differential calculus. But the new thing here, again, is that we are using operators to represent physical quantities. And since we use differential operators to represent physical quantities, we have to deal with the order of differentiation, and then we find that you cannot always switch orders of AB and BA, and here we have this example. And as a result, Px and X, there is an uncertainty relationship between them, and how much is the uncertainty between them? Well, that actually depends on how big that commutator value is. The greater it is, the greater the uncertainty. And if it's 0, when you take h bar equal to 0, everything goes back to classical physics. This is 0, so they become commutative, and we can find simultaneous eigenstates as a result. Then we won't have a problem. We wouldn't have the issue of uncertainty between Px and X. Okay, so in conclusion, we learned that it is impossible to find any simultaneous eigenstates for both Px and X because the operators are non-commutative, and that leads to the uncertainty principle between them, between Px and X. Okay, and without proof, I want to show you a general result between two arbitrary observables A and B, not just Px and X. Suppose the first observer is called A, the second one is called B. I define the uncertainty in A as the RMS value of the measurement of A. What is the RMS value? RMS means root mean squared, right? So just like what we learned in physics 1A, sigma, remember in 1A lab, it's similar definition. I take the value of A, okay, I square it first, then I take the mean value or expectation value of that squared minus the mean value squared. So these are two different things. Here you have to square it first, and then you take the mean value. Here you have to take the mean value first, and then you square it. So they're not necessarily the same. Okay, the difference, take the square root, is called RMS value. You do the same thing for B. Okay, the same thing for B. So you have that. Now, if you define delta A and delta B as such, then it turns out the most general version of the uncertainty principle between these two operators A and B is that delta A, delta B, the product cannot be less than 1/2 of the absolute value of the expectation value of the operators of the commutator of A and B in that particular state. Again, let me say, that's 1/2 of the absolute value of the expectation value of this quantity. What is this quantity? The commutator A and B in this particular state. Now, example. Again, if A is Px and B is X, then we go back to the familiar uncertainty relation between energy, between momentum and position, right? So this commutator equals what? What is the commutator equal to? The commutator itself is always the same. It's always a constant. It's negative IH bar, right? Negative IH bar, the expectation value is also negative IH bar in any state, okay? And you take the absolute value of that, doesn't that become H bar, right? H bar over 2. So therefore, we learned that delta Px times delta X cannot be any less than H bar over 2. Okay, so that is a special case of this general rule. Any uncertainty relation between two quantities, any arbitrary two quantities, A and B. So we have this general rule that applies to any two observables. How do we know that we have to worry about their uncertainty relationship? Just look at their commutators. If the commutators is equal to 0, no uncertainty relation. If the commutator is not equal to 0, then I have this uncertainty relationship. Okay, so we have a new take. We have a new way of understanding the uncertainty relation. It is a matter of representing the observables with their respective differential operators. And Px and X is not the only pair of observables that satisfy the uncertainty relationship. As long as the commutator between any two observables is not 0, we're going to have that same problem. Another famous example is the uncertainty relation between two such quantities. One is energy, and the other is time. Okay, so if you can measure the energy accurately of a particle, you lose track of exactly when it existed. Okay, if you have an exact time window where you capture that particle, so delta t approaches very, very small value, then you cannot have any accurate idea of how much energy this particle has. In other words, delta E times delta T also satisfies a minimum possible value. What is that minimum possible value? All you have to do is to find the commutator between the operator E and the operator T. Now, operator E, as you know, is IH bar partial T, right? We learned that from the beginning when we introduced the Schrodinger's equation, and T is just T. I want you to do this exercise, okay? Apply this commutator with E being the differential operator and B just the number T on any arbitrary wave function psi. Do the same thing that I just did here, okay? For E and T instead of Px and X, I want you to find the commutator between them. And then you plug that into here. I want you to find what is the possible minimum value for delta E and delta T. This is another famous uncertainty relation between these common quantities, energy and time. So you see, the uncertainty relationship is not universal, even in quantum mechanics. In fact, for commutative observables, no such a thing as the uncertainty relationship exists between them. Because the commutator is 0, so delta A times delta B, as long as it's greater than 0, which of course is always greater or equal to 0 by definition, delta A and delta B. So there's no such thing as uncertainty. For example, instead of Px and X, I observe Px and Y, okay? Is it possible for me to find both the momentum X component and the Y coordinate of the particle accurately at the same time? The answer is yes, because if you try to calculate the commutator between Px and Y, you're just going to get 0. You see that? Because I don't care whether you put Y first or put partial X first. When you take this differential operation, it doesn't act on Y because that's not X. Okay? So you can move it back and forth. It doesn't really matter. So you get 0. And therefore, it is possible to know both Px and Y accurately, even though it is not possible to know both Px and X accurately or Py and Y accurately. Okay, now I want to direct your attention to a strange example when it comes to the uncertainty relationship, and that is the so-called angular momentum. We know what angular momentum is, right? Classically, the angular momentum of a particle with linear momentum p, a distance r away from the observation point, is r cross p. Recall that from physics 1a, classical representation. It is understandable that when we go to quantum mechanics, we have to represent the angular momentum also as an operator. Okay, so how do you change it to an operator? Well, r is just r, just like x, y, z, but p now becomes a differential operator. And here is the three-dimensional version of p. Differential operator, we just replace partial x with the gradient operator, which is three-dimensional. And if this is the expression for L, L is a three-dimensional operator. It's got x component, y component, z component. Okay, how do you find the x component, y component, z component? Very simple. All you have to do is take r, write it down as xi plus yj plus zk, and this gradient operator, also write it down in terms of components, I partial x plus j partial y plus k partial z. So you have three terms, cross three terms, you get 9 terms, right? And out of these 9 terms, 3 terms would be 0 because you get I cross I, j cross j, and k cross k. The other 6 terms will belong to x, y, and z directions separately. Then from that, you can find what Lx is, what Ly is, the operator expression for Lx and Ly. Now, after you do that, I want you to show, once you get the expression for Lx and Ly, I want you to show that the commutator for Lx and Ly is not equal to 0. Isn't that strange? Okay, that means it is impossible for us to find both the x and the y components of the angular momentum of this particle accurately. There is an uncertainty relation between them. In fact, the commutator is not equal to 0, and it's not even a constant equal to IH bar LZ. Okay, it's not equal to 0. However, any of these 3 components, Lx, and Ly, and Lz, if you take this component and do a commutator with L squared, which is the magnitude squared, you will get 0, which means it is possible to find the any of these 3 components and the magnitude of this vector at the same time. It is possible to do that. Okay, it's just not possible to find all 3 components separately with accuracy. So here I have this representation of what I just said here. Suppose we are in a certain simultaneous eigenstate for both Lz and L squared. Okay, it doesn't have to be Lz, it can be Lx and Ly, but let's say Lz. So I have the z-axis, right? It is possible to find a simultaneous eigenstate for both of them because, after all, the commutator between these two is indeed 0, right? Now, here is the z component. So that tells me that I know the z component of the angular momentum accurately. I also know the magnitude of the angular momentum accurately because L squared is, we're talking about an eigenstate of L squared as well. So I have this angular momentum. Here's the total vector. Here's the magnitude. Here is the z component. So this angle, okay, this angle is precisely known because you know both the z component and the magnitude here. But that tells me that since I know Lz accurately, I will lose track of Lx and I lose track of Ly because it is impossible to find Lx and Ly or Lz or Lz and X with 100% accuracy at the same moment. Now that I already know Lz accurately, I cannot possibly also know Lx accurately or Ly accurately. What does that mean? It means when you project this angular momentum vector onto the xy plane, you will get an Lx component and Ly component. Neither of these components is precisely known, which means they change all the time given a fixed value of Lz, which means this vector has no choice but to make a turn around the z-axis, because if it doesn't do that, if it's fixed, then Lz, Ly would also be fixed along with Lx and Ly is also fixed along with Lz. That would have violated the Heisenberg uncertainty principle, okay? Because Ln x, Ly do not commute, and Lx, Lz do not commute, and so on and so forth. We will see this picture later when we talk about spherical coordinates in the next chapter, because in the next chapter we're dealing with atoms, and in atoms we will be using spherical coordinate to represent the solution to the Schrödinger's equation, because the potential U, the Coulomb potential, is spherically symmetrical, and you will have to deal with this picture very well because the angular momentum, as you know, would be conserved just like in classical physics, but with a quantum twist, and that is the angular momentum actually spins around the z-axis. It cannot stop doing that, otherwise you would have violated the Heisenberg uncertainty principle.